Hey everyone, welcome to BCP Med. In this video, we're going to dive into the world of hydrogen bonding and talk about what chemical environment is necessary for H bonding. We're also going to talk about the difference between donors and acceptors, what factors influence the strength of H bonding, and several examples. Let's go ahead and get started. When we speak about hydrogen bonding, what we are really talking about is a special kind of non-bonding electrostatic interaction involving polarized hydrogens. Oftentimes, people will describe it as a particularly strong form of dipole force, which is not wrong, but there's actually a bit more to it than that. Like other elements, hydrogens become polarized, specifically positively charged, when they're bonded to a strongly electronegative atom. Because hydrogen can form bonds to almost any element, it's important to clarify that when we say strongly electronegative, we really mean only a few nonmetals, namely nitrogen, oxygen, and fluorine. Why is that the case? Well, let's consider the following electronegativities below. If we look on the left, we'll see that hydrogen has a meager electronegativity of about 2.2, and on the right, we see the elements N, O, and F with their respective electronegativity values of 3, 3.5, and 4, which are all quite high. Now, typically, a bond is considered polar with an electronegativity difference of 0.5 or greater. A hydrogen bonded to any of these nonmetal elements will lead to a much larger difference than 0.5. In fact, we'll start off with 0.8 at nitrogen and move all the way up to 1.8 at fluorine. As a result, these bonds are not simply going to be polar, but will contain hydrogens extremely devoid of electron density, which will result in strong partial charge separation in the form of positive charges on the hydrogen and strong negative charges on the nonmetal, which will be represented also as a strong dipole moment, as indicated by the arrow here in this diagram. We can also visualize this even better by looking at an electrostatic potential map for the molecule butanol, which colors the charge density on the molecule. Here, blue is represented as positive charge density or electron deficiency, and red as a negative charge density or electron richness. The green represents electron neutrality or a zero partial charge surface. Okay. So clearly the dark blue surface on this molecule, which is around one hydrogen, is meaning that this hydrogen is extremely polarized, and that's the one bonded to an oxygen, which the oxygen is colored red for its strong electron density. Notice the rest of the molecule, which involves carbon-hydrogen bonds, is completely green, meaning those bonds are non-polar and there's no partial charges associated with them. So those are not going to have any sort of special interaction. Right? Only the OH is going to have a special hydrogen polarization effect. Now, I thought it would be nice to go ahead and finish up here by looking at the formal definition of hydrogen bonding, that is the IUPAC definition, that a hydrogen bond is an attractive interaction between a hydrogen atom from a molecule or molecular fragment XH, in which X is more electronegative than H, and an atom or a group of atoms in the same or a different molecule in which there's evidence of a bond formation. To sum it up, basically, hydrogen bonds occur when a hydrogen is bonded to an electronegative atom and forms some sort of bond with another molecule. Now, in addition to our strongly polarized hydrogens, there's one more participant in a hydrogen bond, and that is an acceptor for the bond, a region of strong negative charge density, the other pole of the magnet, if you will. Like any positive charge, our polar hydrogens are going to be drawn to regions of negative electron density, specifically the lone pairs on a highly negative species. The species we want as acceptors are going to be either the same N's, O's, or F's that are strong enough to pull away electron density from the hydrogen, or a negative anion, which also has highly concentrated negative charge. For example, in this water molecule on the right, as the oxygen pulls electrons away from its own H's, the electron cloud on the oxygen becomes even more negative and becomes like a homing beacon for other polarized hydrogens in nearby molecules. What happens next is pretty straightforward. For example, let's consider these two HF molecules. We see that the polarized hydrogen of the molecule on the right is going to approach the fluorine of the molecule on the left, which is carrying partial negative charge. In fact, the molecules are going to approach one another such that the positive and negative charges align in a favorable electrostatic interaction, at which point the hydrogen will form a pseudo bond to the lone pair of the negative fluorine atom. Just like any chemical bond is the result of two nuclei pulling on the same electrons, so too is this hydrogen bond. The H and the F in this case are being pulled together by their mutual attraction to the fluorine electron cloud. Although unlike a true chemical bond, the atoms are nowhere near as close, and so the bond is far weaker. Now, remember, due to their original proximity, the hydrogen is still going to be far more attracted to its home electron cloud and its original fluorine atom than this new one. Interestingly though, it is absolutely the case that the hydrogens, being quote-unquote shared by the fluorines, weakens the actual HF bond of the original molecule, almost like the other fluorine is pulling the hydrogen off the first molecule. Indeed, if you look at spectroscopic measurements of hydrogen fluoride in both gas phase and liquid phase, you would find that in gas phase, where the molecule is not interacting with any other molecules in any special interaction, the bond is actually stronger than it is in liquid phase, where hydrogen bonding takes place, because the hydrogen bonding is actually pulling apart the real bond inside this molecule. Another situation in which hydrogen bonding can occur is to a negative anion, like this chloride anion here. This is because it's also carrying a concentrated negative charge and has lone pairs available, as shown by this Mach electron cloud of an anion X-. This happens all the time, such as when a salt is dissolved in water. The water molecule's very positive hydrogen atoms will go ahead and jump onto the anion's negative lone pairs, and this actually is a stabilizing interaction. It helps stabilize the negative charge on the anion now that it's been separated from its cation. And this is why water is such a good ionic solvent, because it can stabilize anions very effectively. Based on these necessary criteria, that is, a polarized hydrogen and a negative acceptor, a molecule can be one of three things: a hydrogen bond donor, that is, it has a polarized hydrogen; an acceptor, that is, it has a negatively charged acceptor site; or it can be both. For example, the water molecule shown here can be an acceptor or a donor, since it has both players. The polar hydrogen can go ahead and latch onto the negative portion of some other molecule, such as the oxygen on this water molecule, while the oxygen on the water molecule can act as an acceptor for polarized hydrogens, like the hydrogen in another water molecule. As a result, water hydrogen bonds very effectively towards itself. There are other similar molecules which are both acceptors and donors, such as most alcohols like ethanol, ammonia, and hydrogen fluoride. An example of a donor-only molecule would be this ammonium ion here. This molecule has some strongly positive hydrogens due to the strong electronegative withdrawing effect of the formerly positive nitrogen. But it has no free lone pairs to accept an H bond. As such, it can only donate one, as it is doing to this water molecule's oxygen here. On the other hand, many molecules can function as an acceptor only. These include any molecules with N, O, or F atoms that have a free lone pair. These atoms themselves do not, and I repeat, do not have to be bonded to another H to work as an acceptor. For example, look at this acetone molecule here. The oxygen can act as an acceptor because it has a lone pair and is sufficiently electronegative to act as a region of attractive negative electron density. However, it itself is not bonded to a hydrogen. It is still an acceptor, right? So this is why acetone is so miscible with water, why it loves to mix with water, because that oxygen acts as a great acceptor for the water-hydrogen bond. Indeed, the caveat is that acetone cannot at all hydrogen bond to itself. It is forever guiding other molecules to a treasure it cannot possess, right? And it's for this reason that mixing acetone with water is so favorable energetically, because acetone cannot itself H-bond with water, cannot itself H-bond with itself, but it can with water. So hydrogen bonds, like any chemical bond, are an energy-releasing interaction, and so when you mix the two chemicals, there's an enthalpy of salvation, which is negative. It's about 0.7 kilojoules being released, and so when you mix these two compounds, you'll actually feel heat being released from the acetone-water mixture for a short period of time. Finally, I want to go ahead and close up our discussion of hydrogen bonding theory by looking at the significance of H-bonds energetically. The energy of a hydrogen bond rounds out at about 23 kilojoules per mole for the water molecule, which is indeed much, much weaker than, say, the typical OH bond of a water molecule, which is about 460 kilojoules per mole. So we're talking a fraction of a chemical bond. That said, the hydrogen bond energy is not trivial. In fact, it's significantly stronger than typical dipole forces, which average at about 10 to 15 kilojoules per mole. Right? It's almost double the strength of many dipole forces. And we can see this effect very clearly if we look at some empirical boiling points. So if we go ahead and compare some period 2 hydrogen compounds with period 3 hydrogen compounds, the effect is very obvious. The period 2 compounds, specifically NH3, H2O, and HF, are going to have very high boiling points as shown here in this data table, right? Especially if we compare them to the period 3 hydrogen compounds. In fact, water is going to have a boiling point almost 200 degrees Celsius higher than most of those period 3 hydrogen compounds. This is because while period 2 elements are very strongly electronegative, and specifically electronegative enough to polarize those hydrogens very strongly, the period 3 elements are only a little bit electronegative. They can polarize the hydrogens a little bit, but not sufficiently to make them latch on to other elements in this parasitic H-bond fashion where they jump onto another source of negative electron density. Hydrogen bonding, as a result, is energetically far stronger than dipole forces, right? We know that electrostatic interactions are strongly dependent on the magnitude of the charges present. Because H-bonding involves very high partial charges, it is going to lead to a stronger electrostatic force than typical dipole forces. This is going to result in much stronger IMFs overall, and thus a higher boiling point. Now, I want to point out also how carbon is totally off left field here. It has a boiling point that's much, much lower than any of the other molecules, and that's for two reasons. Number one, carbon-hydrogen bonds do not H-bond. There is no polarity associated with the CH bond that matters for IMF purposes, and so there's no H-bonding interaction associated with the CH bond. Also, because of the tetrahedral geometry of methane, even if the CH bond were polar, the molecule would end up being nonpolar overall, which means the only forces it has are LDFs. Thus, this molecule is going to be very weak in terms of its IMF profile, and thus its boiling temp is going to be very low. And with that, we've actually reached the end of our discussion of hydrogen bonding theory. Thank you guys so much for watching, and if you enjoyed what you saw, please like and subscribe to the channel. Make sure to check out the other videos on the chemistry playlist to learn more. And if you're looking to branch out, check out our other science playlists as well. See you next time.